What's up? Yeah, look, today we doing last stone weight, which is a heap slash priority queue problem. Okay, so far I finished this pyramid section, and now I went to trees. I really love that part. Array and hashing. It's been so long since I know, but I remember things about uh hashing, hash map, hash sets, arrays, how you push the arrays, how you move the arrays and stuff. Two pointers, I remember this is where you use the left pointer and the right pointer to do the binary search, which is pretty cool. And the sliding window is also algorithm, the left and right, where the right portion keeps extending while the left portion was basically it's like a sliding window where the right portion goes to the right and then the left one to close down things. So it's a pretty cool and linked list as well. I love linked list as well. I think this is the final one I finish and yeah. So yeah, today we're gonna do last stone weight and we're gonna use since hash I'm pretty sure if I go to it again. Yeah, heap. It's a heap stack rather than a stack. So it's heap slash priority queue. So seems the last stone week. You are given an array of your stones where stones on index I represents the weight of the ith stone. We want to run a simulation on stones as follows. At each step, we choose the two heaviest stones with weight x and y and smash them together. If x is equals to y, both okay. Continue until there's no more than one stone remaining. Return the weight of the one last remaining, or return zero if none remain. Stones, 2, 3, 6, 2, 4. Well, technically, smash 6 and 4, and then are left with 2, so the array becomes 2, 3, 2, 2. Smash. So does it mean it takes the bigger one? Yeah, two heaviest stones. Array becomes 1. Uh, 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 oh. Interesting. So you smash one and two, we're left with one. Okay, so okay. I really don't know how to code this, but I guess that's the thing about programming. You don't know how to do it. Maybe the idea can be easy, but can be difficult. So let's at least try to solve it on our own. I'll give it a timer of 10 minutes. And I can always check out the previous question to how to start the heap button. But it's except this one is seriously unknown. Uh, yeah. Well, so will we use heap Q? But I can't really solve this. I have no idea. So I guess we can watch the solution. Then after the solution, we're not gonna watch the code. We're instead gonna watch how it's solved.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem last stone weight. So this is an easy-ish problem I would say, but we're also going to be solving the second version of this problem, last stone weight 2, probably tomorrow or the next video that I upload. So the context is that we're given a collection of stones. Each stone has a positive integer weight, so greater than 0 weight. And each turn, we can choose the two heaviest stones and then smash them together. Now, what happens when we take the two heaviest stones and mash them together? Well, in one case, if they are the exact same weight, both of the stones are going to be destroyed. If they are not the exact same weight, then the smaller stone is going to be totally destroyed, but the larger stone is going to basically be the difference between the weights. So, for example, let's say we had two stones, 5 and 4. This is the weight of the stones. They're not equal, so when we smash them together, the smaller stone, 4, is going to be destroyed, and the larger stone is going to be basically a 5 minus 4. That's what its remaining weight is going to be. So, we start out with two stones and then we get reduced to a single stone. The smaller stone gets destroyed. The larger stone is going to be 5 minus 4. That's a 1. So that's kind of what happens when we smash two stones together. At the
Oh
end,
yeah, I wonder how will we queue it based on the weight of the stones. Will we use binary or
there's going to be at most one stone left. And it could technically even be 0 stones if there aren't any left. So, what do we want to return? We want to return the weight of whatever stone happens to be left over. If we don't have any stones left over, then we can just return a 0 as the default value. So, I will say that this problem is somewhat straightforward. Let's take a look at one of the examples. And the reason this problem is straightforward is they gave us basically all the instructions and the information that we need, and all we really have to do is kind of simulate these instructions. We don't actually have to find a clever way to solve this problem. We just have to simulate what they told us. That's pretty much the best we can do. What did they tell us to do? They told us to always take the two heaviest stones and then
no?
smash them together. How are we going to get, suppose we had a bunch of stones like this, how are we going to get the two heaviest stones? Of course, we could sort the array. That's one solution. But even if we did sort the array, you'll find that it's a valid solution. But when we're taking the two heaviest, 7 and 1, we're smashing them together, and then we're going to basically be introducing a new stone, right? So 8 minus 7 is going to be the new stone, 1, and then we're going to maintain the sorted property of this list, we're going to have to insert this in order, which might be a little bit annoying, but I think it is a valid solution. But another solution is going to be using a heap, not a min heap in this case, but we're actually going to be using a max heap because we're going to be taking the max stones each iteration. In order to take this input array and transform it into a max heap is actually an O of n time operation with the heapify function, but every time that we want to actually get the maximum from here, that's going to be a log n operation. And how many times potentially are we actually going to need to get the maximum from here? N times, so n multiplied by log n, that's what's going to be the overall time complexity of this solution. Now, how is it actually going to work? Well, basically, as I mentioned, we're going to simulate. So we're going to assume we have a max heap here. We're going to get the largest stone. It's going to be an 8. We're going to get the second largest stone. It's going to be a 7. We're going to smash them together. We have 8 and 7 smashing them together. 7 is smaller, so this is going to be destroyed. 8 is going to be transformed into a 1 now, so we can, let's just introduce another 1 to this list. And we're going to continue the simulation, right? We're going to get the now two biggest stones. It's going to be a 4 and a 2. What's going to happen with 4 and 2? Well, 2 is smaller, so that's going to be destroyed. 4 is going to basically be 4 minus 2, which is going to be 2. So we can insert that into our max heap. So now we're going to insert a 2. Now we are left with, it's a little bit messy, but we're left with a 2, a 1, and a couple 1s. So when we smash these two together, we're actually going to be left with a single 1. I won't draw that because I think at this point you probably get the idea. Then we're left with 3 1s. What's going to happen with these 3 1s? Well, 2 of them are going to be smashed together, and then we're left with a single 1 left, and we have nothing left. We have no other stones to smash this 1 with, so when everything is said and done, we will be remaining with a single stone, so we can go ahead and return 1 as the return value. And, it could have been a little bit different. It could have been something like, okay, we're left with 2 1s, then they get smashed together, and then we have nothing left. So then if we had nothing left, we could return a 0. But that's not the case in this example. We do end up returning a 1, as you can see down here. This problem is pretty straightforward if you have a decent understanding of heaps and their time complexities. In this case, the only tricky part for us in the code is going to be Python does not actually have max heaps, so we're going to have to use a min heap to basically simulate a max heap, and you can do that by basically, assume we had some kind of heap, we would want a heap, and you can do that. We're going to have to use a min heap to basically simulate a max heap, and you can do that by basically, assume we had some kind of heap, we would want 8 to be the maximum value, and then suppose we had some other values, 3 and 5. But this is how a real max heap would work. But if we are actually implementing this with a min heap, it's going to be the opposite of this, but we still want 8 to be the value that we get from the root. So what we're going to do is actually have negatives we're basically going to multiply every value in the heap by -1 so that the minimum, which is 8, -8 in this case, is going to be popped when we want the maximum. And then when we pop this, we're going to get -8, but we can just convert it. We can get the absolute value of this and then just convert it back into an 8. That's kind of how, unfortunately, we're going to have to do this in Python. In other languages, I think you can just get a regular max heap. But I think that's all the information we need. Now we can hop on into the code. But before I do, let me just give you a very quick word from our sponsor for today, interviewing.io. If you want to get hired at top tech companies like Google, Facebook, and Amazon, then you need to check out interviewing.io. Okay, so now let's get into the code. Like I said, we're going to be writing the simulation for this problem. And so the first thing we want to do is put all of these stones into a max heap. Now Python does not have max heap, so we're going to put these in a min heap, but we're going to multiply every one of these values by -1. We're going to make them negative. So in Python, what I'm doing right now is basically just going through every single stone and putting it into a list and multiplying each stone by -1. I'm putting the negative of that stone in this list. And now I want to turn this list into a heap. So what I'm going to do is heapq.heapify this stones. This is a linear time operation. So now we're good to go. Now we can start running the simulation. And remember, we want to continue this while the number of stones is greater than 1. If we have 1 stone or if we have 0 stones, that's when we can stop the simulation. But until then, we are going to take the 2 largest stones. How can we get them? Well, we're going to pop from the min heap. We can do that like this, heapq.heap_pop from the max heap, not min heap. So pop from stones, and that'll give us the largest, and this will give us the second largest stone. And remember, if the stones are equal, that's basically, we wouldn't have to do anything, right? We just remove these 2 stones from the heap, and if they are equal weights, then we don't really have to do anything. We're not going to add them back to the heap. We don't have to do anything. But in the other case, if the second stone that we popped was less than the first stone that we popped, and why am I saying second stone? Well, because the second stone is going to have a smaller weight than the first stone, or equal weight, right? Because when we're popping the first one, that one is supposed to be the heaviest stone. But we're doing it this way, but remember, we made all the weights negative. So what we actually have to do is the opposite of this case. If second is greater than first, suppose we popped, this is kind of an example. Suppose the first stone had a weight of 8. In that case, it would have a value of -8. And the second one had a weight of 7. And the value would be -7 in that case. Then, of course, -7 is a greater value than the first stone, right? So that means basically this second is the smaller stone, and we have to destroy second. And how are we going to do that? Well, basically, we already popped it from the heap, so we don't actually have to destroy it. All we have to do is take the difference between these two and then add that back into the heap. Now, how are we going to take the difference? First of all, heapq.heap push is how we can actually add to the heap. So we're going to add to stones, whatever that value is. How are we going to get the value? Well, obviously the value in this case would be a 1, right? If we took an 8, subtracted 7 from it, we'd be left with a 1. How can we do that computation? Well, basically you can just take second subtracted by first. If that kind of confuses you, if these negatives and kind of that math confuses you, you can convert these into absolute values if you want. So, you can take the first and second and convert them into the absolute value. Then the math will be straightforward. I don't really want to waste, too much time writing that code out, and this kind of does make sense to me. So I'm just going to keep it short and concise. I'm just going to take second subtracted by first, which will give us the weight that we want to add, right? We want to add a stone of weight 1. But remember, in our heap, we are keeping track of negative values, so I would have to multiply this by -1. The easier way to do this is just to take first subtracted by second, which will give us the exact same thing. It'll give us the negative value that we're looking for. It'll take the difference between these, and that difference will be negative, right? We'll have first, which is -8, plus 7, which is going to be a -1, which is what we want in this case. So I hope that makes sense. It's a little bit confusing, but basically this is our case, and that is the entire simulation code. Once we're done with that, we can go ahead and return whatever the value of the stone happens to be, the remaining stone. So stone at index 0. But don't forget, we actually do have negative values, right? So when we return the value of that stone, we want to from the air into the heap air absolute values if you want. So you can take the remaining stone. So stone at index 0. But don't forget, we actually do have negative values, right? So when we return the value of that stone, we want to return the positive value. So we're going to take the absolute value of this stone. And also don't forget one last edge case. What if stones was empty, right? What if we didn't have any stone left in here? Well, one way to handle that edge case is just to take, before we return, just say stones dot append a 0. So in that case, if there's already a stone in this list, we'll end up returning a don't forget one last edge case. What if stones was empty, right? What if we didn't have any stone left in here? Well, one way to handle that edge case is just to take, before we return, just say stones dot append a 0. So in that case, if there's already a stone in this list, we'll end up returning that stone because it'll be at index 0. If there's not a stone, then we'll add this 0 stone, and then we'll end up returning that 0 instead. So this basically works out in all cases, which is what I'm getting at. So I hope this was helpful. a stone, then 0. So in that case, if there's already a stone in this list, we'll end up returning that stone because it'll be at index 0. If there's not a stone, then we'll add this 0 stone and then we'll end up returning that 0 instead. So this basically works out in all cases, which is what I'm getting at. So I hope this was helpful. As you can see, this solution does run.
Right. Goodbye. Thanks for watching. Before I go, at least I guess this gave up some ideas on how heap queues work. I know that this is the heapify, the heap pop are functions for Python, and yeah, I guess if I can explain it. These are basically how do I say, hidden, so you don't really know what it does. It could be complicated, and basically it's just a function and contains stuff that is saying this. I forgot that word. Word. Wait. Let me ask Irish. Yeah, abstraction. Basically abstracting like how this was done. Just you just know that it works. So yeah. And I guess if I want to explain this, we initialize the stones. We put a negative S for each S in stones, make them negative. I think pretty sure. And we create a queue between the stones, which is our negative. This is a min heap. We don't have max heap, so yeah, we're using min heap with this one. You sure? Oh, there's also sorting. There's binary. Oh, I can also do binary search. What? Yeah, yes, it's pretty helpful. And and yeah, each time we basically just keep push the second minus first. Yes, even since they both are already pop, we're gonna push the sum of both second and first. I mean the subtraction of second and first, and we just return the absolute value of it. It's technically negative, but yeah. Thanks for watching.